share. All right, so a few announcements before we get started. Announcements. I posted homework 5 a little bit late, so Monday. So the first two problems, which are actual problems, are going to be bonus homework points. So they are short problems, just to get you to do a little bit. You should be able to do them with the videos that I posted on Monday. And the second problem, you actually need to look at the slides, not just the video. So that it's not exactly the same as I did in the video. But I think the first problem pretty much, yeah, I forgot what the first problem is, but it should be very simple. And then the second problem, part of it I did in the videos on Monday, and part of it is in the slides I didn't do in the videos. That one is gonna be due on Monday. So if it hasn't been changed, I will change it. I'll ask KU to change the due date. And that's the penultimate homework. Then there's a last homework, homework 6, which will involve some coding. And that one will be due Friday, a week from this Friday. And that's gonna be it for homework. Yeah, so that's homework. Then we have the Abacus exam. I actually wanna say something about the Abacus exam. How did it go? Okay, not okay. I'd say one thing, because I don't think anybody did it this way. You know, you were free to do however you want, but the easiest way of doing setting up the problem was with symmetric boundary conditions, and do an eighth of the. It's fine if you didn't do it like that, but the easiest way of doing this type of problem is to do the. Does this look like a? Well, this should be an eighth of the. So, you know, if there's this doesn't look like a pressure vessel. You know, if this is the pressure vessel, basically, you just need to cut an eighth of the pressure vessel. This is so just an eighth of the pressure vessel. And then do symmetry boundary conditions on each of these. Like this one, for example, would have, if this is X, this is Y, and this is Z, then in this plane right here, you use symmetry in X. In the plane at the bottom, so this one, you would have symmetry in Z. And then in this last plane, you would have symmetry in oh, sorry, this is Y, this is X, and this is Y. Whatever the plane orthogonal to the axis. That would have saved you basically, instead of the whole mesh, just an eighth of the mesh. And the thing is symmetric, right? So it has these symmetries. You can flip things around and you get the same thing. So did anybody do that? I don't think anybody did. No. But in the future, if you have a problem with symmetries, use the symmetries, because it saves you a lot of computing power. Saves you a lot of the mesh. That's one reason. And then another reason is you really don't have to think much about boundary conditions. because you can just use the symmetric boundary conditions in Abaqus for each of these planes. And that's it, and then you apply the load. So otherwise, then you have to think really hard about, what point do you fix?
Yeah, I was just going to talk about that. So if we did the full model and I didn't apply any boundary condition.
That is okay in this case. So in most cases, so I would say, let's say you do the full model. Then you do have the question of what is the boundary condition that you should apply. And here it works if you don't apply any boundary condition, and it's the same as the symmetric boundary condition. So here works with no boundary condition. But this is almost always doesn't work. Why? Because you have, this doesn't prevent, so in this case it's fine. Abaqus doesn't complain because the loading is symmetric. So Abaqus doesn't complain because loading is symmetric. But in principle, the error that you might get, you are likely to get, is they are not preventing rigid body motions. And so if the loading was not symmetric, then the thing would, would drift away, and you will not find the equilibrium, because there's no unique equilibrium if you don't fix at least a point. So I think what you should have done here to make sure that it doesn't just fly away. It doesn't if you don't put boundary conditions, but if you don't want it to fly away, you need to fix at least one point completely in X, Y, Z. So you need to at least fix one point. And that actually reduces 3 of the rigid body motion modes. So it reduces the displacements. It doesn't reduce rotation. So this can still rotate freely. So if you want to prevent complete rigid body motions, you can fix extra points in special ways so that you still allow all deformations to happen, but you prevent rigid body motion. So for example, this thing, if you just fix a point in the edge in the center on the left, that one, then now the vessel cannot move. But if, for example, it can still rotate around this axis, right? So if you don't want it to rotate, then you need to pick any other point that is not aligned in that axis. So let's say that this is the axis. So you need to pick some other point, let's say this point right here. And for that point, all you need to fix is just 1 degree of freedom so that it doesn't rotate. So let's say that this is the x-axis. So for this point, I would just fix in x. So now I have fixed all the displacements by fixing the point on the left. And now if I just fix x for this point down here, then I'm preventing rotations in that direction. And there's 3 rotations, so you need to fix 2 other degrees of freedom. So let's say that you also don't want this rotation, right? So then you will pick, for example, this right here, and that one you would fix in, let's say this is y, you would fix in y. So with that, for example, if I fix all 3 degrees of freedom for the point in the left, only x for one of the points in the bottom, only y for one of the points at the other end. Now I've prevented rotations, I prevented displacements, rotations in this axis, rotations in the other axis. And then the last axis that I have is this vertical axis, so rotations in this axis. And so for that, again, just pick another point, and then, I mean, you can pick either the same point and just fix it also in x, and that would prevent rotations in the You can fix this one also in X. And that one will prevent the last set of rotations. So technically, this boundary this is not the unique way of specifying, as long as you think about, which points and which degree of freedom to prevent rigid body rotations, then it should work. It should uniquely eliminate basically rigid body motions. So this will be the proper way. This case, it works even if you don't do that, because the loading is symmetric, so things don't drift away or the thing doesn't just rotate around an axis freely. So we'll take that. But in general circumstances, you want to at least fix 6 degrees of freedom, basically rigid body motions. That's why, because it's more difficult to think about what do you want to fix. I would say that, especially for this type of example, if you can use symmetry, it's much better, because then the symmetry takes care of everything. If you do the symmetry of the 3 planes, it will fix all the rigid body motions.
So this is off the thing, but if that were a real model we wanted to predict, and it had 4 legs in the bottom, would you still go for symmetry, or would you actually model the whole thing with the legs?
Depends on how the legs connect to the pressure vessel. Yes. So if they're actually fixing, a point or a set of points in the pressure vessel to the floor, then you would want to include them. And then yes, it will not be symmetric if they actually fix it to the thing. Now, most of the times, it wouldn't be like that, because it would introduce stress concentration. So it would basically, even if it's kind of fixed, probably the flexibility of the supports is greater than the pressure vessel, so that the stress concentration doesn't go to the pressure vessel. So it won't be really fixed to the ground. Other questions? Yes. Is the exam 1? No, because I don't want the TS to grade the exam, so I'm gonna grade it, but I haven't had the time. I was traveling over the weekend. But I'll grade it, so therefore have a little patience on me, but I'll grade it. Other questions? All right. Well, I think that was the aside from that, which I think was the not obvious thing. I didn't expect. I thought maybe someone will think about that, but it's not obvious. So I really have to bring it up, that when you can, simplify, and if there's symmetry, use the symmetry. Aside from that, I think the rest of the process should be basically your standard lab exercises. So you have to measure. You can get a hex mesh, but if you got a TED mesh, that is okay, as long as you do the mesh convergence. So as long as you generate multiple meshes and make sure that your stress basically reaches a certain value. So that was, I haven't looked at the reports, but I would say, even if it was TED mesh, which is okay, obviously you can do partitions to get nicer meshes, hex meshes, but TED mesh, okay. You can do partitions to get hex meshes. Even if you use TED meshes, the key thing is that you do mesh convergence. That one is, this one I've said it multiple times, but you have to make sure that your model is fine enough such that the stresses that you care about are not changing widely when you refine the mesh. Did you do mesh convergence? No.
We were asked to do it.
We were asked to? Okay, good. Good, because it's super important. I think that's, obviously there's ways in which you can get better behavior by, like I said, doing only an eighth of the domain, because then you need a smaller, you have a smaller domain, so you can actually refine your mesh more. If you do hex dominated, you probably get better convergence. Dead meshes usually require more elements. That's it. Aside from that, I mean, this is a nice problem. There's not much bending. Is mostly in plane. Stretching is a little bit of bending, but it's not bad. So I think, you know, even the reduced integrations probably do okay. I don't think they show any unstable mode. What else? There's an analytical solution. That's another thing, you know, kind of contrasting with the project, for example. For this case, really a finite element is not needed for the ideal pressure vessel. So for that one, you can just compare to analytical solutions. When do you actually need the FE? When it's not exactly the ideal case, when you have some other features that you want to include that are not the perfectly cylindrical shape, when you have some sort of imperfection that you want to account for which you don't have an analytical solution. But, you know, starting with the one for which you have an analytical solution is a good way to make sure that your model is doing things correctly. Then you can modify that to include the imperfection that you're interested in. Okay, so that's one thing for the exam, the Abacus exam. Other things. Well, the other thing is, can you do it with a shell? Yes, but we didn't really use shells, so absolutely no need to use a shell element. But again, shells save you computational power. So here, you probably need a few elements. Maybe I'll say, I haven't looked at your solutions, but I would say typically if you have a single element through the thickness, that's not very good. I don't think that should converge. You should know that from the beam bending examples that we did. Don't use a single element through the thickness, because you cannot capture really the variation in normal stresses for when you have bending. Even if it's a little bit of bending, you can just not capture it. So don't do, I don't know if you did that, but so typically you need, just like the cantilever beam example, you probably saw how many, depends on whether you use quadratic or linear. So depending on quadratic or linear, you might need more or less elements. But definitely one is not enough. So hopefully you didn't use one. I just say, remember the cantilever lab. Things can go wrong if you don't have enough elements through the thickness. So mesh convergence, enough elements through the thickness, eighth of the domain, extra ways of saving computational power. You can do an axisymmetric simulation. We didn't really use axisymmetric, but you can use the axisymmetric elements in Abacus. That also saves you, but then you only need to do the plane. But we didn't do that. But just for you to know, other ways of simplifying model is to either use shell elements shell elements are specially constructed so that you can use only a single set of elements through the thickness. Then it's okay. Single element through thickness is fine. That's the whole point of the shell elements. But the formulation is different. So shell elements have a formulation that accounts specifically for bending. So for that one, the whole point of the shell elements is that you can use just one element through the thickness. If you use solid elements, you can't. So that's a way of simplifying the model, but we didn't cover it in class, right? Definitely did not expect you to use it. And the other one is axisymmetric. If you use axisymmetric elements, you can do just a 2D simulation. So all you need is a plane. And yeah, and that one works. Again, not expecting you to know about axisymmetric elements, but for the future, if you ever have to run a model that is axisymmetric, then there are axisymmetric elements in Abacus, so you can try to read the documentation to use them. Very similar to the solid elements or plane stress or plane strain elements. So they are basically all you need to do is specify that it's axisymmetric, and that's fine. That's all you need. I think that's it. I think that's it for the exam 3. Any other questions? Was it hard? Okay, was it hard? Yes. 2 hours, okay. Good. All right, so that's one thing. Then other announcements. So homework announcement, exam overview. For the project, I had one person asking whether or not the problems that I put at the end of every homework count towards the final report grade. They don't. They are just homework problems, and the bar to get those homework points is really low. Like if you are doing something, we are giving you the points throughout the homework. All I want is that you are making progress in your final project so that it doesn't come to the last week and then suddenly you have nothing and then you are starting from scratch. But it doesn't, all those homework points are homework points. They don't count to the report. The report is the report. And for that one, the hard will be a little bit higher. So for, if in the homework, I ask for the contour plot and then you kind of do the contour, but it's not quite correct, they will still give you points. But in the report, I do want to not just see effort, but I want to see whether or not things are correct. So that's just, because someone was asking me. Did anybody else ask anything? No? Cool. And then the last thing that I can think of is course evaluations. So please do the course evaluations. I might do some sort of bonus as well for that, but I'm not exactly sure where can I put bonus points. Maybe not homework, since I'm doing homework 5, problems 1 and 2 as bonus. So I think about that, where it makes sense to give a couple of bonus points for course evaluations. So ask me again on Friday, and then I'll have an answer for that. All right. So if there's no questions, we'll move on to the topic of today, I know in the syllabus I say quadrilateral elements, but then I was looking at the notes on Brightspace and I have nothing for quadrilateral elements. I have basically just more practical considerations. So I thought I would just go straight into that. Sort of just giving you pointers as to when do things go wrong in Abacus, for instance, and how to solve those problems. So I'll do that today, and I'll do that on Monday and Wednesday of next week. Friday we'll do definitely some Python, but I don't think I will do kind of more theory than we have done already today, Monday or Wednesday, more practical considerations, so a little bit more overview style. This is the strong form of linear elasticity. This is the weak form. We've done that in previous lectures. But what I want to talk a little bit about today is, again, how do we make sure that we are using Abacus correctly? A reminder that verification is the process of determining that the code is actually solving the equations that we want, and validation is the process of determining whether or not the model actually matches reality. A few requirements for making sure that the model makes sense. So if you are using Abacus and you are doing stress analysis, when can you use the linear elasticity assumption? So in Abacus, we haven't done this, but there's an option for nonlinear analysis that we haven't checked. We've always done linear analysis. So when does this assumption break? That if you do a linear elasticity analysis, it just won't match reality when strains are larger. So linear elasticity works really well for strains that are small. So if your strain is around 1%, then you are absolutely safe. If it's greater than 1%, then you are not as safe. And definitely if it goes above 5%, I would say I would not do the linear elasticity example at all. But for small strains, definitely below 1% strains, you are okay. You can use the linear elasticity. Even 1% can be a little bit large depending on the material. I mean, a lot of the steels and metals will already have yield by that point. But some materials will have yield. Another thing to check when you run your model is, let's say you're doing some analysis with some aluminum part, and then you compute the strain field and the stress field, and then you want to make sure that you are within the elastic region. So if you remember your strain stress plot, usually will look pretty linear and then it will fail, right? So typically they will have, it will yield and then it will fail. So it will look linear, then it will yield, and then it will fail. So there's a linear region. So you want to make sure that when you're looking at your results, that your strains are all within that linear region, and your stresses are also within that linear region, right? So if you go in this region right here, this is already to the right of this. Then you can have yield or fracture. So clearly you cannot just use the linear elasticity assumption. So you have to, but after you run a simulation, make sure that you are still within the linear region of the material. Another type of model that you can do is you can do a dynamic model. You can do the static problem. We have only been doing static problems in the class, which works well if the inertial forces are at least an order of magnitude or less compared to the external or internal forces. And by estimate accelerations, what I mean is that I don't know if for this year, I don't remember, if anybody had a project that involves some impact, like a baseball bat or something like that. But in that case, the inertia is not negligible. So if you have sort of shock problems, problems with really high accelerations, then you cannot use the static analysis, then you have to do a dynamic analysis. So at least do a back of the envelope calculation to estimate the accelerations in the material to determine if there's going to be significant vibration associated with the analysis. If the accelerations are small, so if the initial forces are accelerations times the density, if those are an order of magnitude less compared to the external or internal forces, then it's okay. But I would do a quick check before I go for especially if you have something that is moving, before you do a static analysis. Yeah, again, make sure it's within the elastic region. And then, again, also this type of problem will not tell you if things fail. Like if the linear elasticity analysis will only tell you if things are within this region, it will do its job. But if it's out of that region, then you don't know, you cannot trust it. So if you do the simulation and you get that the stresses are, like here, you might get a stress that is not even realistic for the material, because it might just be, extrapolating that linear response. And then you say, oh, the stress is so and so, but that just doesn't make sense because that material cannot withstand that stress. And therefore, really, as soon as you move out of that linear region, then the analysis is no longer valid. You neither need to include fracture, include the nonlinearity, include plasticity. So all these other things that happen when things fail. Ideally, most of the times, why is this still useful? Because most of the times you want everything to stay within that linear region, right? So in that case, if you get something that goes out of the linear region, rather than trying to do the nonlinear analysis, probably what you want to do is you want to change your design, change the material so that you are within the linear region so that things don't fail. A few characteristics of the solution. So that's kind of just even before you start. Then what to expect for this solution. This type of elasticity problem is called an elliptic problem. No need to know exactly where that comes from. But this will always give you smooth solutions. So regardless of what the forces look like, you will always get a smooth contour. It will not be able to capture things like shock, or for that you need to use elastodynamics. So you need to actually solve the Newton, force equals mass times acceleration. If you want to get any sort of shock wave propagation, then you won't be able to get it with the equations that we are doing. The equations that we're doing always will give you a smooth solution. The equation is symmetric. No matter which current transformation you make, you get the same equation. This is just for computational. This is something internal to Abacus. You don't really need to know this. But one of the nice things about the elasticity problem is that it's symmetric, which just makes it very computationally efficient. This symmetry can be broken if you have some different types of coupling with other physics that we haven't talked about. And when you break the symmetry, you need to worry about not just computational costs, but also stability. But for our purposes, we don't need to worry about that. There's the Samenan principle that perturbations smooth out. This one is actually important, which means that do you need to have this one is very important. I'll just, what do I mean by perturbations fade away? So let's say that you have some very complicated part. I don't know. You have some very complicated part that you are analyzing. I don't know what this part could be, but you have some super complicated part. Do you really need to make the mesh of this part capturing every single detail? Maybe not. Why not? Because this Samian principle that perturbations smooth out. Let's say that the loading is in this end, right? So that if you make and you are interested in stresses in this region, right? So you're interested, for example, you know that there's going to be some stress concentration here. So this region is where you want the most, this one you really want to preserve. So geometry and mesh here is super important. But you know, regions here, the stresses are going to be low and they're not going to be changing much. Do you really want all the detail here? No. So if you don't solve the exact problem, but you solve an approximate, let me see if I can. Let's say that instead of, oh no, it's going to delete everything. But instead of this, you smooth this out. Even more, I mean, it will be pretty robust. Let's say that you have something like that. That will affect your solution, yes, but it will, so you will get a change in the stress here for sure. You know, maybe it looks something like this. So it will change, but it will not be, it will be small. So the effect of that change decreases as you move away from some change, but it will not affect the stress far away. So that is very important, that as you move away from where you make changes, the effect of those kind of dies down. So if you perturb things, it will affect things locally, but as you move away from that region, the effect will die down. And so you can use this to simplify sometimes your geometry. If you don't need to mesh or have detailed geometry everywhere if you don't need to. That also saves you computational power. Then another one that you should be on the lookout for, this is very important. I don't think we ever did, but point forces lead to singularities. So avoid putting a single force in a node. So if you put a single force in a node, it will kink the node and you'll have very large stress. So distribute, and because it's not realistic, right? So in most cases, you never have an exact point load. In some cases, okay, it will not break your model, but I would say avoid putting point forces. Try to do you know, a small patch, like put tractions. So instead of point forces, I would, you know, put a few a few forces. Any questions? This you can use in your project. Plane stress, plane strain, or axisymmetric. When possible, simplify the problem. Obviously, if your problem is 3D and there's no way of doing anything but the 3D model, then just do the 3D model. But in many cases, you can get at least a good approximation with a 2D problem. So there's 3 classes of 2D problems. There's the plane stress problem that typically applies when things are very thin. So when things are very thin, then the stresses out of plane are generally small compared to the in-plane stresses. And therefore you can ignore what happens out of plane and just do a 2D simulation. This is what you did for the plate with a hole lab 3, I think. So plate with hole lab. You did plane stress. Plane strain is the opposite. Planar strain is when you have really thick structures where there might be some stresses out of plane, but there's so much material out of plane that it really won't fail, right? So then in that case, what you assume basically is that there's no strain in the out of plane direction. Yeah, and then again, you also worry only about the stresses in the in plane. So that works typically for thick structures. So in the limit of, as you make the structures thicker and thicker, then the better your plane strain approximation becomes. And another class of 2D problems is what I just said, axisymmetric problems. So whenever you have an axis of rotation, then you can just do the 2D simulation, and it looks very similar to what you do for Abacus. You pick either plane stress elements, plane strain elements. You can pick axisymmetric elements, and so you have just a 2D mesh. So again, simplify whenever possible. This I've shown, and I think this is homework problem 1. I think this is problem 1 of the homework. The Stevens matrix changes a little bit, but that's it. You just look it up. Shape functions are the same that for scalar problems. I mean, this is just to show that for triangles and quadrilaterals, there is the choice of linear, quadratic, cubic elements, just like we have before. You have done examples with linear and quadratic. We've never really used cubic elements. I think I've said this before. Quadratic are good in general. I would say quadratic are very good because they give you more flexibility and you don't need super fine meshes. But linear are also very useful. The only thing that you might need, as long as you do mesh convergence analysis, you'll be fine. Just linear will require finer meshes than quadratic, but it balances out because the quadratic elements require more computation per element. So they tend to balance each other out. I would say, yeah, I don't have a preference between linear and quadratic. I think quadratic, again, generally they do really, really well. So that would be sort of my first goal. But linears are fine. As long as you do mesh convergence, you will be fine. For tests, you also have linear, quadratic, cubic. The shape functions are the same as before. So they are with the Lagrange polynomials. As you increase the degree of the polynomial, they might become a little bit unstable. They might become a little bit wiggly. So that's why typically no more than quadratic, because the bigger the polynomial, the more wiggly it is. Which is not good. So that's why typically just typically I just stick to linear quadratic. These are 3D hex. I think you've done that. We have done this in the lab with a cantilever beam. Reduced integration tends to be the default option for Abacus. When you create your mesh, it will always select this reduced integration because it wants to save computational power. And it's okay, but you have to be careful. Sometimes it will break your model. You've done that for the cantilever. If you do reduced integration, you get nonsense. I'll just scroll through the example. So what happens when you do reduced integration? You can get this type of trapezoidal shapes. And these are when you see, I'll show a mesh below. When you start seeing these patterns where you have like this inverted, you get, it's called hourglass modes actually. Because this looks like an hourglass. When you start getting these alternating where you see a lot of hourglasses, then that means that you are basically having the type of deformation where you don't have sort of resistance. You can see another hourglass mode here. So look for this type of shape. That's what, I mean, it has a name, hourglass modes, because you see this type of hourglass. So when you see something like that and you're using reduced integration, that means that something is not correct. And you need to either switch to full integration or add stabilization. Abacus has some built-in, reducing hourglass mode options that you can click when you select elements. But again, I think what I want you to know is to be on the lookout for these patterns. When you see a lot of these hourglasses, then something is wrong. Or when you see this type of scaly pattern, for example, this is with a normal integration, this is with reduced integration. And you can see that you will start getting kind of weird things. This is with normal integration, this is with reduced integration. So again, you see sort of these scales, think something is wrong. So be on the lookout for those. And I think that's about it. We are out of time. I'll come back to incompressibility on Monday. I'll just give you a lot more tips on Monday and Wednesday, what to look for,